There's a data center sitting on the seafloor off the coast of Scotland right now. It's been down there for years. It's a sealed metal cylinder about the size of a shipping container filled with servers, and it's doing what data centers do, processing data, storing information, keeping the internet running, except it's doing it underwater, in the dark, with fish swimming past the windows. That's not a science fiction premise. That actually happened. And the reasons why it happened, and why floating and submerged data centers are becoming a serious conversation across the entire tech industry, tell you something important about the infrastructure crisis hiding underneath the AI boom that almost nobody is talking about. Starting with a fact that sounds mundane but has genuinely enormous implications. Computers get hot, not just warm, not uncomfortably warm. The kind of hot that, if you don't aggressively manage it, will cause hardware to throttle its performance, make errors, and eventually fail entirely. Heat is the natural byproduct of computation. Electricity flowing through transistors generates it, and the more computation you're doing, the more heat you're generating. Now scale that up to a modern AI data center. A large facility training and running AI models might contain tens of thousands of GPUs, graphics processing units, each one drawing hundreds of watts of power and kicking out significant heat continuously, 24 hours a day. A single rack of AI accelerators can draw as much power as a house. A full data center might draw as much as a small town. Managing that heat is, depending on how you look at it, either the central engineering challenge of running a data center or just an enormous ongoing expense, or both. The systems you need to keep servers at safe operating temperatures are expensive to build, consume enormous amounts of energy themselves, and in most traditional facilities, consume staggering amounts of water. Here's the number that tends to surprise people. A large data center can use millions of gallons of water per day for cooling. Some estimates put major hyperscale facilities, the kind run by companies like Google, Microsoft, and Amazon, at consuming enough water daily to supply tens of thousands of homes. That water goes through cooling towers, evaporating to carry heat away from the facility. Most of it doesn't come back. In a world where water scarcity is becoming an increasingly serious issue across large parts of the United States, in Europe, and elsewhere, that's not a small problem, and AI is making it dramatically worse. The compute demands of training and running large AI models have pushed power and cooling requirements to levels that would have seemed extraordinary even 5 years ago. So when engineers started looking at this problem seriously, some of them landed on an idea that initially sounds absurd, but actually makes a lot of physical sense. What if instead of spending enormous resources to generate cool air and cool water to bring to your computers, you just put the computers somewhere that's already cool? Like, say, the ocean. The most notable experiment in this space is Microsoft's Project Natick. It started as a genuine research question. Is it feasible to deploy data centers underwater? And eventually became a real-world test. In 2018, Microsoft lowered a sealed cylindrical vessel into the water off the Orkney Islands in northern Scotland. Inside were 12 server racks containing 864 servers and the associated networking gear. The whole thing was plugged into an underwater cable for power and connectivity, and then left alone on the seafloor at about 117 feet of depth. It stayed there for 2 years. In 2020, they pulled it back up and evaluated the results. The findings were genuinely interesting. The servers inside the underwater vessel had a failure rate about 8 times lower than servers in a comparable land-based data center. 8 times. That's not a marginal improvement. That's a fundamentally different reliability profile. The reasons why are worth understanding. When you seal a cylinder, pump out the oxygen and fill it with nitrogen, which Microsoft did. You remove one of the major causes of server failure, corrosion from humidity and oxygen exposure. You also eliminate the mechanical stress that comes from constant temperature fluctuations, which cause materials to expand and contract over time and gradually degrade connections and components. The temperature in the cylinder stayed remarkably stable because the ocean around it acted as a massive, consistent thermal buffer. And the cooling itself? The cold seawater did most of the work passively. The heat generated by the servers transferred through the hull of the cylinder into the surrounding water. No cooling towers, no evaporated water. The ocean absorbed the heat and distributed it through its own enormous thermal mass, a heat sink so large it barely registers the addition. The efficiency numbers were compelling. The power usage effectiveness, a standard metric for how efficiently a data center converts electrical power into useful computation, was significantly better than comparable land-based facilities. Now, underwater cylinders are one approach, but they're not the only one, and in some ways, they're not even the most practically scalable one. There's a parallel conversation happening about floating data centers, facilities mounted on ships or barges that sit on the surface of the ocean rather than underneath it. The appeal here is somewhat different, but related. Ships can move, which means a floating data center can theoretically be positioned wherever ocean conditions are most favorable. Cooler water, lower energy costs, proximity to offshore renewable energy like wind or wave power. Some concepts involve anchoring near tidal energy installations or offshore wind farms, so the data center is powered directly by renewable energy and cooled by the sea it floats on. There's also a regulatory angle that's easy to overlook. Building a data center on land requires navigating zoning laws, environmental reviews, utility negotiations, and a dozen other jurisdictional processes. A vessel in international waters or in specific maritime jurisdictions exists in a different regulatory environment. For some operators, that's a meaningful consideration, not because they're trying to dodge responsibility, but because the permitting timeline for land-based facilities has become genuinely prohibitive as demand has surged. Google filed a patent years ago for a water-based data center that would use wave motion to generate power and seawater for cooling. Whether that specific concept ever gets built is almost beside the point. The fact that major tech companies are seriously engineering these ideas reflects how acute the problem has become. But here's where it gets complicated, because this isn't just an engineering story, it's also an environmental one, and the picture is more nuanced than it might first appear. On one hand, ocean-cooled data centers genuinely do reduce freshwater consumption, which is a meaningful environmental benefit. They can also achieve better energy efficiency, which means less carbon emitted per unit of computation, particularly if they're paired with renewable energy sources. On the other hand, introducing warm water into marine ecosystems isn't automatically benign. Ocean ecosystems are sensitive to temperature changes. Marine biologists have raised questions about the thermal plumes that a large-scale underwater or nearshore data center might create, and what those might mean for local fish populations, coral ecosystems, and other marine life. Microsoft's Project Natick was small enough that this wasn't a major concern, but extrapolating to industrial scale raises legitimate questions that don't yet have fully settled answers. There's also the question of what happens when hardware fails and needs to be replaced, or when an entire facility reaches end of life. Retrieving and recycling underwater infrastructure is not straightforward. The logistical complexity of maintaining, upgrading, and eventually decommissioning underwater server facilities is something the industry is still working through. None of these concerns are necessarily fatal to the concept, but they do mean that the future of ocean-based data centers isn't purely a function of engineering elegance. It's going to be shaped by how the industry navigates environmental relationships and regulatory frameworks that are still catching up to the technology. What makes this story worth paying attention to is what it reveals about where we are in the AI era more broadly. The narrative around artificial intelligence tends to focus on the software, the models, the capabilities, the applications, the risks, and opportunities. All of that is real and worth discussing. But underneath all of it is a physical infrastructure problem that is becoming more challenging by the month. AI requires computation. Computation requires power. Power generates heat. Heat requires cooling. Cooling requires water and energy. And all of that requires land and permits and time and money. The companies building AI at scale are not doing it in some frictionless digital realm. They are building physical things in physical places, drawing power from real grids, consuming real water, generating real heat. The constraints of physics don't disappear just because the product is software. Throwing data centers into the ocean, or onto it, is one of the more creative responses to those constraints. The fact that it's being seriously explored and that early experiments have yielded genuinely promising results says something about how real the pressure has become. Whether the seafloor becomes a standard location for AI infrastructure over the next decade, or whether it remains an interesting experiment that points the way to less dramatic solutions, is genuinely hard to predict. What's clear is that the cooling problem isn't going away. It's getting larger as AI models grow more powerful and the demand for inference at scale continues to climb. The servers are already in the water. The question now is how many more follow them and what we learn in the process.